would be to just show a few view graphs to introduce the topic. My name's Hal Puthoff. I'm director of the Institute for Advanced Studies in Austin, Texas. And since 1985, we've had a very intensive program, both theoretically and experimentally, on new energy concepts. And so we have an ongoing budget, engineers working in the laboratory every day, many patents for various devices. And so we feel like we're making reasonable progress. And one of the requirements we have is that the work be of high enough quality that it can get published in mainstream literature. So we've published many papers in Physical Review in the United States, which is the toughest of the journals to publish in. So it is possible to present these ideas in the mainstream. Even one of the papers that we published last year in Physical Review had the title, Extracting Energy and Heat from the Vacuum. And so that was accepted. I and a colleague from IBM worked on the energetics and the thermodynamics to show that there was no violation of either to pursue this concept. As we all know, there are problems with fossil fuel sources which we presently use, pollution byproducts. There's certainly problems with the nuclear power plants, especially in the United States. There's now essentially impossible to build a nuclear power plant. So people in the energy industry are out searching for alternatives. And of course, some of these are familiar: solar energy, thermonuclear fusion. In the beginning, thermonuclear fusion looked like it would be a great boon, but you're probably familiar with the joke that goes around: thermonuclear fusion looks great about 15 years in the future, but then it's always looked great about 15 years in the future. Capillary fusion is a different form of fusion that may work. There's a lot of controversy about so-called cold fusion, under non-thermonuclear conditions. But the one I'm going to talk about, which I think has great promise, is a so-called zero-point energy extraction. I'll explain what I mean by zero-point energy. It really is the energy of so-called empty space. The concept of empty space has gone through several shifts over the past couple thousand years. For example, Democritus said empty space was a void. Otherwise, how could there be room for the atoms to move around in? But then Aristotle came along and said, no, empty space must not really be empty, because we have heat and light, and it must propagate through something. Finally, this was codified last century by Maxwell in electromagnetic theory, saying, well, if electromagnetic waves are waves, then like water waves, they must have something to propagate in, so there must be an ether. But then in special relativity, when attempts were made to try to measure velocity through this ether, it couldn't be done. And so with special relativity and the Michelson-Morley experiment, people said, okay, there is no ether. Empty space is really empty. But then it was only 10 years later, Einstein himself, in developing general relativity, ended up having space-time that could be distorted and warped. And by the time he got finished describing what general relativity had to say about space, with all these properties of being warped and distorted, Einstein himself said, well, then space isn't empty. Introduced the term metric, but basically that sort of brought the idea of a full space back. So Einstein didn't really get rid of it except for a few years. Then finally, with quantum theory, that's when it became absolutely clear that empty space was not empty. There are vacuum fluctuations, particles come out of the vacuum and then annihilate and go back into the vacuum. So it's now recognized by quantum theorists that empty space is very full, very active. What do I mean by that? Let's say we have a case of, say, a mass in a spring, you pull down and you let it go like that. Or say have a kid on a swing and you give him a push and let go. Classically, we say that the thing will eventually come to rest. The oscillator will come to rest. It comes to rest because there are losses in the system and energy leaves the system and eventually it will come to rest. But quantum mechanically, we say that's not the case. That if you excite an oscillator, or you push a swing or a pendulum, you do anything like that and let it go, losses will reduce its energy, but it only comes down to a certain minimal amount of energy, and that energy remains. And so everything at the microscopic scale is always fluctuating. In fact, it turns out that, and it's been calculated, in this room, there's enough energy in that volume to evaporate all the world's oceans. And that's not a controversial idea or a fringe idea. In standard quantum mechanics, it's recognized that the energy in even a coffee cup is enough to evaporate all the world's oceans. John Wheeler's calculated, Richard Feynman's calculated it. The question is, can we get at that energy? And for a long time it's been thought probably not. But as I'll go through in my presentation tomorrow, there's been a history of development where we see that you can get at that energy. Now you might ask, there's all that energy right there, where does it come from? And we know where it comes from. Every piece of matter in the universe is fluctuating around, doing its quantum dance. And in so doing, it radiates energy out. And then every other atom is sitting in that radiation field and absorbing it, and that causes it to jump around and therefore radiate. So it's basically the electromagnetic equivalent of putting a microphone by a speaker and getting the squeal. The particle fluctuations generate the fields cause the particles to fluctuate, and you can do the calculation and show that that accounts for where the vacuum fluctuations come from. It's a giant cosmological feedback system, and we've published that in Physical Review, the details on it. Now you might say, if there's all that energy, even right here in the room, why don't we notice it? Well, in fact, we do. Experiment any of you can do to prove that that energy is really there. Suppose you're on a bus or a train. It takes off with a jerk and you fall back on the floor. What is the force that knocked you down? I mean, it's a big force. It knock you down. Well, it's that as the train or the bus tried to accelerate you, you ran in to the wall of vacuum fluctuations. And there was a resisting wind from the vacuum that held you back and knocked you down. And it turns out that that resistance to accelerating through the vacuum energy is proportional to acceleration. So unlike ordinary wind, if you're just moving at a constant velocity, you don't feel it. But if something tries to accelerate you, you do feel it, and it holds you back. And so the reason Newton's law says force equals mass times acceleration The reason that when you apply a force you get an acceleration is that you have to apply a force proportional to acceleration in order to overcome the vacuum energy holding you back, which is also proportional to acceleration. So actually there's no more ubiquitous constant phenomena. Every time you move your hand, you feel the vacuum. So the energy is very palpable. We just published this in Physical Review in February of this year. And so it was very well received. There was a 2-page write-up in Science Magazine and also in Scientific American. And those are very conservative publications in the United States, and yet still they were interested and published about it.
Does this close the loop in terms of a universal theory?
Well, from our standpoint, the vacuum fluctuations do provide a unifying
Field
theory. I've already shown in earlier work that gravitation can be accounted for, and gravitational mass can be accounted for on the basis of interaction of particles with the vacuum fluctuations. And then in this paper we found that the inertial mass came out to be the same as the gravitational mass, and that's known empirically, but from a philosophical standpoint it's never known why the inertial mass and the gravitational mass should be the same. And the answer is they both arise from interacting with the vacuum fluctuations, and it fixes them to be the same.
This has to do with the thermal noise.
No, that's an addition. Who asked the question? Right. That's an addition. When you write down what is the background in the universe, you get 2 terms. The one term is a zero-point energy. The other term is a thermal background distribution. The reason the zero-point energy is called zero point is because if you let temperature go all the way to 0, the thermal term will disappear. But at the 0 point, this first term, which we now call zero-point energy, remains. It doesn't depend on the temperature. So the term 0 point and 0-point energy means 0 temperature point.
So you would have 0-point energy at absolute 0.
At absolute 0.
And in the absence of anything else.
That's right. So if you go in the furthest vacuum of outer space and you're hoping to power your spaceship on 0-point energy, you would not have a problem.
Dr. Puthoff, you may know from my papers that I doubt the equality of gravitation and inertial acceleration.
You say you doubt it?
I doubt it, yes.
Doubt it, right.
I have from various observations, stellar observations. Can be because the density, let's say, or viscosity of the ether changes as a result. Also, this equality may change.
Okay, well in our modeling,
Yeah.
I would agree with the first part, and that is if the density of the vacuum fluctuations changes, these will change.
Because
But in our model, they change together.
what I have only calculated only is already a deviation of 36% for the Jovian moons. That close already.
I see.
Think it over.
Okay. Now, what we're interested here is extracting this energy for use. Now, it's a well-known false idea in physics that, well, we have all this heat energy around us. Why don't we somehow extract that energy for use? But you can prove that it just doesn't work. It would take more energy to get the energy out of the surrounding heat than you would get. And so when it was recognized that 0-point energy was there, it was thought that similarly it couldn't be extracted. But a researcher at Hughes Laboratory pointed out that there was already an effect in the laboratory which demonstrated that the 0-point energy could be extracted. It's a so-called Casimir effect. Casimir effect is named after Heinrich Casimir, who was research director for many years at Philips Laboratory in the Netherlands. And this is what he noticed. As you know, if you have a, say a radio, transistor radio, and you take it in your car or go inside of a metal building or inside of a shielded cage, you can't hear the radio stations. The metal shields out the electromagnetic signals. Well, these vacuum fluctuations are electromagnetic signals. And so Casimir realized that if you had a metal enclosure, or say even just a couple of metal plates together, close to each other, that the region in between would be somewhat shielded from the vacuum energy coming from all different directions. It would be somewhat shielded. Well, this energy has radiation pressure, momentum, energy, just like any electromagnetic wave. So between the plates, where some of that energy is shielded out, the energy traveling back and forth puts only a certain amount of radiation pressure outward. But outside, where there is no shielding, you have all the energy pushing in by radiation pressure. And so what happens is that the plates are pushed together. And this is a large force, and it's been measured in the laboratory. The force goes up to 1,000,000 newtons per square meter at close distances. Well, a newton is the weight of a book. A square meter is about a square yard. So it's a big effect. In certain cases, when you bring metal tips down close to pieces of metal, for example, in electron beam machining, this force is strong enough to pull the metal tip into the material. And in industrial processes, you have to use strong servo mechanisms to keep it away. So this is a big effect. Well, what a researcher at Hughes realized was, okay, if I put up two metal plates in outer space and I walk away, those plates will get pushed together faster and faster and faster and faster until they finally hit. And when they do, that generates heat. So you've actually converted some vacuum energy into heat. And you can trace that it doesn't violate conservation of energy. You can trace bit by bit where the energy comes from. The energy comes out of the vacuum, starts to push the plates together. As they get closer and closer, more and more modes are shielded. The energy, vacuum energy that was in those modes, has now gone into the kinetic energy of the plates moving together. Closer and closer, more modes excluded, more kinetic energy, and then when they hit, the kinetic energy is turned into heat. So there was a proof of principle, absolutely acceptable in mainstream physics, that the vacuum energy could be tapped. Now the question is there some way to tap it efficiently?
Question.
Yes.
Is the fact that you take two highly polished surfaces of metal, put them near each other, and that
Right.
Like
That's part. That's right. That's
that
part
of it.
That's part of it.
Okay. The other is
There are some charge effects on the surfaces too.
Surface effects.
That's when they go together. You can't pull them apart. You have
Exactly.
to do that.
Exactly. You have to do it this way.
Right.
Yeah.
And since lasers have been invented, people always have these very polished optical flats in lasers. And again, when you put them together, you can't pull them apart. You've got to bring them apart. That's partly this effect. So the question is there a way of getting it out efficiently? So far, there are three ways that are known to extract the energy in an engineering sense. The first is electromechanical, and this was published by this researcher at Hughes, and he even applied for a patent called a vacuum fluctuation battery. I don't know if he got the patent, but he applied for it. His idea was, well, instead of letting the plates come together and make heat, I will charge the plates electrically. And then as they come together, they will build up a strong electric field. And then you can use that field to drive current through a battery. But it's not practical, because the amount of energy you get and the difficulty in dealing with them so close, it's just not practical. But In our laboratory, we're working on two additional methods. Instead of having plates come together, you can also have a cylinder which is squeezed, or you can have wedges which are pushed together. In other words, anytime you have surfaces near each other that can control the vacuum modes, you will get this kind of pressure force. And so in addition to like squeezing a metal boundary, it's also possible to make a plasma, a little lightning discharge in the laboratory. Just a high-tech version of scraping your foot on the rug and touching the doorknob and getting a little spark. And it turns out that if you meet certain conditions on the density and the voltage and so on, then you can get this effect to squeeze a plasma as well as pull metal together. And so that's one of the approaches that we're looking at, generating little lightning bolts in the laboratory. They condense the charge. By the way, it leads to a whole new technology, condensed charge technology, which we have 18 different devices patented. Medical x-rays, fast computer chips, flat panel displays, microwave generators. There's a whole series of things that come out of just having this condensed charge. But the energy thing is the one that we're pursuing most dramatically in the laboratory. There's also another phenomenon called sonoluminescence. And for those of you who have been interested in research with water, this is pretty interesting. If you have a turbulent fluid, have bubbles in the fluid, this vacuum pressure force will collapse the bubbles. And it's now been studied in the laboratory that when those bubbles collapse, they put out an intense burst of light. In 50 picoseconds, you can get 100,000 photons out of one little bubble. And Julian Schwinger, who's a Nobel Prize winner in physics, has shown that this energy comes from the Casimir effect. In other words, this is a conversion of vacuum energy into another form, in this case, light, heat, radio waves. So we know of a laboratory that has some experiments going in which they were creating turbulent bubbles in fluids and then measuring the energy in the water by the heat, and they were getting over unity efficiency. And so we have now arranged to have those devices shipped to our laboratory, and we're going to do a very detailed study. But in this case, we're talking about kilowatts of excess energy.
Not 1 watt.
Right, kilowatts. Now, people often think that, well, if you come up with a new energy idea, the oil companies will squash you like a bug. It's not true. That myth, I don't believe, is true. Once we had our laboratory results, we applied for our patents. One of the first things I did, I went to Pennzoil and I briefed the president, Scotty Holland, president of Pennzoil. I went to Texaco and briefed the research director. I went to these oil companies and told them about the potential of this new energy source. What would be the response of their corporation? I didn't tell them we had it, just in case the negative people were right.
You may never come back.
But I said, it's possible in principle, what would be your response? Their response was, we would absolutely welcome it, because their resource is running out. When they draw small amounts of it out of the ground and make drugs and plastics and nylon, pharmaceuticals, they don't use up much of the resource and they have a large profit margin. But when they draw it out of the ground and dump it in automobiles and dump it into heating your house, it uses up an enormous amount of the resource and they have very little profit. So they said they would be glad to have some other energy source come along and take this burden from them. They said the way they see it, it's as if you were heating your house by burning Van Goghs and Picassos. Really ridiculous.
Good analogy.
They also said that if these new energy sources come along, they would be the first to invest in them to make the refineries more efficient. So I think the myth that they'll stop you just simply isn't true. We've worked out our own development strategy to avoid difficulties with competing with other industries. For example, you might think that the Mideast would not like this development, even if it was okay with the refineries. But the way to overcome that is to go to the Mideast people and ask them to underwrite the new development, so that can pull the plug on their potential competition. The nuclear industry also does not have to be threatened by the development of these sources, because you can go to the nuclear industry and say, you've got your magnificent billion-dollar plant here. We're not going to bother that. What we want you to do is pull out those nasty radioactive rods and throw them away and drop in our new devices. And then you can go to the public and say, we have gotten rid of radioactive pollution and we're reducing the price to the consumer. So it could be a big win for the nuclear industry, and they can continue to use their power plants.
Are it possible to build one yourself and put it at your home and cut off your wires to the electricity?
I'm going to talk about that in a minute. Right here, skip the generator in the garage stage. We think, although you could, we think it would be better not to do that, and I'll try to explain why. With the electric power utilities, the way you keep from threatening them is that you don't want to have everyone have one in the garage and unplug immediately, because the economic chaos would be too big. But the electric power utilities are having to meet increased capacity requirements all the time, and in the United States they must satisfy a Clean Air Act, which is very difficult. And so you go to the electric power industries and say, okay, as you add new units to meet increasing demand and need to meet clean air requirements, don't build more of the old kind, just add our form. Because let's face it, even if we had generators up and running, it would still be a couple of decades before you could get them all distributed around anyway. So we think you'd skip the generator in the garage stage, and instead you'd go to a TV manufacturer, you would go to a washing machine manufacturer, a dishwasher manufacturer, and say, okay, on your next new model, instead of having a plug that plugs in the wall, have these never say die batteries in the back. And so that way, as units become obsolete, new units get introduced without plugs, and so you slowly unplug from the utility companies instead of doing it all at once.
Yeah, because economically, most people are not going to go out and buy all new equipment.
That's right.
They'll do it as their old equipment wears out.
That's right. So I think that's the way to approach it. And of course, there will always be special purpose things which special units can be built for, and those will just develop as they develop. So, and of course, at the conference, I will give some more of the technical detail without making it too technical. But so, what's the present status realistically from our standpoint? First of all, it's scientifically sound. This is not pseudoscience. The Casimir effect is a real effect. It's known to extract energy from the vacuum. Absolutely accepted by physicists. It's certainly embryonic in development, because I'm sure none of us arrived here today in an automobile powered by zero-point energy. So it is definitely early stages of R&D. When investors come to us, and we do have investors in our laboratory, we tell them it's high risk, infinite payoff. So, but it is high risk. So if you want to invest money in something that you know will make money in the next 5 years, maybe you wouldn't invest in this. But if you want to live your old age out as a trillionaire, maybe you would. So for workers in the field, our feeling is that just as the 20th century may go down in energy terms as the nuclear age, we think the 21st century will be the zero-point energy age. That's our view. I'll be glad to answer any questions, and we can just open it up for discussion because there are other people here who know a considerable amount.